Thank you, Paul. Thank you, Matt. It's a really wonderful talk. I enjoy very much. Now it's my pleasure to introduce the third speaker, Zhigang Wu. Zhigang is a professor at the Huazhong University of Science and Technology. Before joining HUST, Zhigang was an associate professor in microsystem technology at Uppsala University, Sweden. The mission of Zhigang's group is to developing the new fabrication and manufacturing technology for liquid-fused software intelligence system. It really done wonderful job. Today is going to share us his latest story of this software intelligence. Zhigang, the stage is yours. Zhigang, you ready? Please turn on your microphone. You mute. Okay, here we go.
Thank you, Alice, for your kind introduction. Today, I would like to share some of our recent work on liquid fused software intelligence. Liquid actually is a very unique material. So you can say it's continuous deformation under the pressure, and also in you immerse you in the liquid, you will get a very, very nice conformity. And also the carrier can carry a lot of nutrients, materials like soil, something. And also, our planet, the Earth, most area is widespread with what one of this material. And also, this liquid as an essential part of our natural intelligence. So I give an example from left. So we have the liquid is the essential part for the energy nutrient delivery system. For example, for this transpiration in the plant, we use water to deliver the nutrients and also deliver the waste out. For example, we absorb this carbon dioxide and also emission oxygen. And in our organism, we also have this similar system like our blood, our circulation system. And also, besides this kind of energy or nutrient delivery system, and also it is an essential part of intelligence. So here I show example is mimosa. The mimosa actually is just kind of liquid actuation. They just deliver some kind of liquid into common cells to get this instant response from our finger touch. So another system I show is very high intelligence. For example, our brain, as our brain is very dependent on the neuron. The neuron actually is the ion conductors. So we can actually is the movement of ions. So this also liquid also plays an essential with this very advanced digital intelligence. So liquid also offered our new opportunities for it to make a new kind of intelligence. So in the left side, I show this work. I think it's quite inspiring work from Stephen Quick. I think it's about 2 decades ago. I show you this logic for the liquid to make this huge circuits. This can be compared to with the IC industry. And another I show is one is from Matt Group at Max Planck. I show this mimically this bacterial behavior in autumn. And another kind of liquid also can be some kind of a medium to induce intelligence. Here, this one I showed a work from Rob Sheffield from Cornell University. I used a kind of liquid battery to make a drive this kind of robot fish. And the right one, they use this machine is kind of liquid can be driven is very, very small, very, very light, is 8 to 8 milligram micro robot. So here the right corner I show is work from MIT. They use this kind of plant hybrid. This plant is very nice. So you see here, this movie you show here. So when you touch this kind of plant, this can be like this sensing, they can always guide transfer to another kind of plant. They can be response next. It's like verify. We can always guide our electrolysis. So here I want to share my group work something part of this kind of work. The first part of work I will majorly focus on the liquid alloy. Then another part where second part will show the liquid fused software robot. So we can come to first one. About the decades ago, white side group I found is very interesting is liquid alloy. So at the same time, when I was in Uppsala, and at the same time, when we find this one, we can use this very special liquid alloy and introduce it in microfluidic chip. So we can make this kind of stretchable electronics. However, the problem is this kind of capillary filling is very low efficiency and also is very slow. So as a guy work on long-term with on the manufacturing, I'm wondering, is it possible can we transfer this kind of scalar process if we can make this mass production like this fluorescent printing, like printing a newspaper, very fast continuous. And recently, we're wondering, is it possible we can make this kind of printing to 3D dimensional shape? So the first one, I want to share my work with the first group on the mask printing. So when a decade ago, we tried with this one, we think it's possible we can use this mask printing. For example, when we make this custom make the t-shirt to print this nucleoid, and actually we tried, it worked. So first we prepare a slab of peanut mass, then we use this kind of station mask. So we can use this roller to print liquid alloy on this one. Then we can deposit the active section on this one. Then we use another kind of layer of peanut mass to cover this one. So this is the device what we can get. So when we use this stretch under this stretching cycle up to 20% or a maximum to 60, so this can work. Say it works quite well. Unfortunately, we found the problem. So we come here. So use this stencil. So this stencil we made is from metal. So this metal should be made very thin. But when we use a few times, it's very easy to break. So we think, even this break, why we try to make just use one single time? So this time we introduce one kind of tape. We use this polymer tape to use the mask. So at the same time, we use this kind of semi-cured PMS. So we combine this kind of technology. We can use the tape to transfer this mask to onto this semi-cured PMS. We can make this device work again. So this will show this FID, we can work this one. And very, very important, so we solve another problem is we can make any pattern on this surface. Because you know, when you make this stencil, you have to, the structure should be suspending here. If you have a circular shape like this one, so you already can't get this one. But if you use tape to transfer this one, so you can get any shape on this kind of pattern on this kind of liquid alloy. So we made the performance one. You can see this we use a reference for this rigid one. So we nearly can get the same performance as the rigid ones. After that, we found this is work very well for this kind of tape transfer printing, but the problem is we can't work many kind of surface. It's the second issue. The second issue is the surface usually is very roughly. We can't control the thickness. So we try to think if we could find another method. So this time we found another method is we use atomization printing or use spray printing. So we use this tape transfer transfer the mask. So we use this mask printing. spring. So we work on this very nice well polished transfer device. So we found this kind, US introducing this kind of atomization, we can work on many kind of surface. For example, we can work on this half-killed PMS, full-killed PMS, Ecoflex, another kind of PMS or PMMA, polyamide, and also you could say even if we can work on these very, very low surface energy material, for example, Teflon. So this is very, very advantage. We can work on lot of kind of surface. We can work on lot of target now. Then we find another problem is we use this tape mask. So usually we need manually remove this kind of mask. So it's quite annoying, and also is I think is a bit of a bottleneck if we want to make Scala make this one. So then we find another solution. So we try to change this kind of mask. So we use this kind of change this material into water soluble material. For example, EVA. So this kind of material, this kind of glue used in our backside of stamp. So this can be dissolved in water. So we make this one. We first print this kind of liquid oil on this face. Then we put this on the liquid. So this mask can be automatically removing. So continuously we can make this kind of, for example, mask patterning and spring, and also what remove this kind of mask. We can make this to roll press like this printing newspapers. So this we show work a few works with this sensory. If you want to make this many kind of movement of your finger, the finger, the skin is very soft. So you don't want to interface the movement of your finger. So this can be, because we use a liquid alloy and it's the anterior deformation. So you can see here, we can nearly exactly follow the movement of our finger. More important, you can see these small three movies. You can see the wrinkle formation of this one. So we're very excited. This one we can work very earlier. So you can see recently a group from Tokyo University, they also published seminar. This gave me a great encouragement. This means our liquid alloy will be find something extremely useful, some advantage on this kind of sensor without interference. Okay, so as we talk about, so we want to work on some this very fast printing technology. It's exactly like this flexography printing. So we continue this one story. So about 5 years ago, in our group, we find a very interesting phenomena. If we add very, very tiny amount of additives, for example, PIE, into the cyclical PMS precursors A and B's, we can significantly change the PMS property. Especially, we can make this sticky. So you can see here, if we attach our this modified PMS on its surface, it significantly stick on its surface. So we found this kind of because it's a bit different from the per sample we add some dilution PMS. So actually, it's the formation some kind of double network inside this PMS. Can we make this PMS stretchable and sticky and also very soft? So after expansion, we work on this find a kind of new way for synthetic transfer printing. So micro contact pad can be used for transfer printing many dedicated components. It's very uh, it's very nice work. Is dominant and also demonstrated by the John Rogers group at the UIUC, now in Northwestern group. But this group, this process is is very non-process, as you see here. So you can say you need to make a lot of process to make a pattern, select this pattern. So make a first select pattern to make this space pattern and transfer to another one. So, but our group, we found this one. If we can use this kind of sticky PMS, we can make this group much faster. So here is our solution. So we use this kind of laser to cut this kind of patterns. Then we use this sticky PMS. We can stick this directly select this kind of pattern from this kind of surface. We don't want to have this so many patterns to define this kind of structure exactly which kind of pattern we needed for the future. Very, very surprising for us. We can select any pattern we can like we see here. So we show the view of video we see here. So we can select the two of these one, and also can select three of these quarter line on this one, and also fourth, and also can select all of this one. So we can make it very convenient to select any specific pattern in our substrate. So we can make this selection or transfer printing is more efficient. Then we carefully study what kind of happened for this kind of selective transprinting. So we found it's very, very important to control the energy release energy between the donor and the stamper, and also the donor and the stamp and your between stamp and donors. So it's very important to control the energy is between this overall transfer printing and non-transfer printing for this one, and also uh, different from the traditional approach. We just control the speeding, control the pinning speed. We can control many kind of ways. For example, we can control how much additives we add in this kind of substrate, and also we can control this curing time and temperature. So which can be very, very useful. So then we study all of kind what happened in this fluorescent graphic printing. Actually, we found this is kind of a mechanism between the competence, the energy between your substrate, the plate, and your ink. So you can say we got this plate, we make this one surface is one is olfactory and one is hydrophobic one. So this one can selectively to add some paper, adhesion, some water on this one. So they can when they put on this ink, the ink only cover this kind of surface. So it can be get very fast printing. So we inspired for this one, so we can get how to make this printing this liquid alloy. So here we show this kind of a process. You can see here, after we can use this kind of liquid alloy, we try to get this one. So we put this liquid alloy on this one term. So we remove this one, so you can get this kind of liquid alloy. So we can transfer to PMS very easily. So how we can do this one? Actually, the PMS actually is very like this PMS liquid alloy. But the problem, how we can make this surface is don't like this liquid alloy. That means liquid alloy phobic surface. After we tried this one, we found we use laser can make this kind of surface happen. So you can see here, if we use laser to treat this surface, So the nucleoid will automatically rebuild and rolling away, but another one without treating may just stick on its surface. So we can use this one to make this whole printing happening. So this way, carefully study what happened for this after treating of this PMS or carbon dosed PMS. So you can see here, after we treat this kind of PMS, we can get a very rough surface. And when we made this kind of contact angle between this nucleoid and treated surface, we found the after we treatment, get this one, the advanced contact angle and receding is very narrowly distributed. That means this very liquid alloy phobic surface. So we can get this fast respel this liquid alloy. But another part, without this treatment, the difference between this advancing contact angle and receding angle is very large difference. That's the trend to stick on its surface. Okay, you can see here, right? And more importantly, this kind of control, this kind of contact angle or liquid alloy phobic behavior can be controlled by many kind of these optical needs of operational parameters. For example, the scanning difference, the scanning speed, and also laser spot. Many kinds of can be control this kind of surface. So let's say we think, hey, we can try to print many kind of patterns from this one. So we can get about the narrowest width is about length width is about 20 micron. Here we show about 40 micron, and also the space about 40 micron. And also we can try to print many kind of planar surfaces like this triangle, star, hexagon, and circle, and also very complex like this Chinese knot. And surprisingly, we found this kinds can be worked on this 3D surface. For example, this pumpkin, and also we make this 3D printer, make this kind of arbitrary 3D space. And also we can, as a flexible printing, we try to repeat use our stamping. We found this way can be, our stamping can work about 100 times with high robotics. And also our received example, we made this kind of stretching cycling for about 50 percentage stretching. We can get about 10,000 times recycling without apparent degradation. And also this can be worked on many kinds of substrate, for example, PMS, glass, carbon PMS, and vinyl tape and PET as well. So here we show a few example. We make this demonstration. Here we show is 46 LED matrix. We can show this is can be well deformed and show without functioning. And also we can make this kind of new kind of, for example, this strawberry model. We can make this concave with this device can be conformally. Even with this stretchable, we can use very reliability for this kind of device. So, and also, I know we want to work this automatically. So with help of this kind of robotic arm, we can make this progress automatically. So after we make painting, we try to make this one. How we make it is 3D dimensional integration, because you in the second you need to work on multi-layers. So a group from a student from my group find a very simple issue to make this via, that means multi-layer connection of multi-layers. How to make this one? Actually, you know here, make this carbon PMS. So we can make selectively to make this some of this area is nickel alloy phenolic part. So the liquid oil will automatically deposit this one. So we use the spray gun to push this one, so make this break up this one, it can be automatically connected. So use this kind of method, we can get this connection of this video, like 2 seconds. So here we show this one, the video, we show this one. So here, so we can make this liquid alloy on this liquid alloy. So here we connect this one. So this is resistance very high, right? Without a spring, without a gas spring. So here next time we try to use this gas spring. Wait a second. Now we use this gas spring airflow. So you can say it can be the resistance is not, it's very small now. So that means we can get this automatically connect these two layer of these circuits. So use this kind of technology, so we can make a largest device with this kind of technology. So here we show a sensor can attach it to our arm, which to show to measure the temperature, humidity, and also it can, and also since and also with movement of also. So you see here, so we can attach this kind of sensor on our arm, so we can introduce water. You see, we find instantly we use the mobile phone, we find that this humidity increased and also the temperature is decreased. So this show a potential we can use our nickel alloy to make this wireless device and also wearable device can be controlled or connected to the internet. So as I talked, so the set story, we want to work on the tender or three-dimensional printing. We use the hydroprinting. So the plant actually play an important role in agriculture. It can be save our food and energy, and also it can be for scientific research to make medicines for disease or something. And so very importantly, I think MIT very recently MIT show a new nice idea. They can be used plant hybrid to make highly intelligent systems. So I also is inspiring this kind of work. We also want to try to work on some kind of use our liquid alloy to work on this one. But when we started this kind of try to work on this, make this liquid alloy on liquid, we found it's quite challenging issues. First of all, the plant also is complex. They have very complex shape. For example, urine is undeveloped surface and also individual. Everyone is different. And also is tender, is far vulnerable to damage, heat, and pressure. And also is susceptible to medical constraint and easily affected by constraints. And also is dynamic, quite dynamic, is dynamic large deformation in the behavior and in the growth. And also, when we tried this, we found another challenging issue. Actually, the plant or leaves or stems or trunk, they have very tiny micro nano surface structure on this surface make this trouble. So I will talk this later. So when we try to make more flexible graphic printing on this liquid alloy on this surface, we found problems. But when look for literatures, we found a nice way to make this hydroprinting is very wide to use on the industry to make a conformal structure, especially for this 3D surface. This can be used in this water surface commodity and also is milled in temperature and no regiment is soluble sacrifice layer. So we try to combine this kind of demand actually is quite matched to each other. So we think maybe it is a good candidate. We use this kind of hydroprinting to make this liquid alloy on this plant surface. So we design this kind of method to make this. We named the liquid alloy based morphine electrolysis. So the first step, we try to spring or print a liquid alloy on these water-soluble films. Then we put in this water. Then when this kind start to dissolving, we put this plant. Here we use the bean sprout to immerse into this one. Then we pull out gently out with PVA gel on this surface. Then we wash away this residue. We can get this one. We can make this manipulation or do something research. Here I show this video in this process. So we first get this printed this liquid alloy on this water surface. So the PVA start to swelling and to dissolving. Then we put our target on here. So on the surface, then we move it out. Then after wash out, we get this kind of nicely print on this surface. Okay, so we found this can be work on many kind of inorganic surface. So we can put a lot of lines and the strips on this semi-sphere surface. And also we can make this array on surface, circular lines, and also this zigzag lines on surface. And also we can make this functional vertical pattern on this kind of surface. So here and also we can make this 360 degree to rotating this kind of surface to get this integrated circuits on this kind of surface. And also we can make something amazing, we think. Is when we can make this is a transparency we use for projecting. To say we can make this circuit on the both sides of this transparency. You see, this is the top surface. This is the top surface, and also at the same time, we can make this circuit printed on the bottom surface. So we can make this workable for this LED lighting on something. And also, we find another very, very interesting thing is we can print these liquid alloy patterns inside something containers. Here I show is a decant is a swan next together. So we can print our universal logo inside this kind of surface on this cafe surface, and also on this wine glass water, wine glass, and also this kind of another kind of decants is like this very belly, big belly. We can print this our universal logo on this belly inside in the surface of this belly decants. But when we try to work on these plants, we found some problem. So when we try to these bean sprouts, we can print very nicely the pattern on liquid alloy on these bean sprouts. But when we work on these rose petals and lily petals, the problem comes. So we found it's very difficult to print a very nice pattern on this kind of petals. We found the problem is this kind of have a very nice micronano structure. They make this doesn't work. So when we try this one, so these petals, we use the microscope to learning the contact angle. So we put this liquid alloy on its face. When we remove this kind of needle, so they will need very fast follow this kind of needle. Then occasionally we found the water can happen in this one surface. So when we put a drop of this water on this petal of the rose petal, so we found when we put this kind of liquid alloy, approach the surface, then we stick on this surface. It's very, very fast return. So we test this one. We found the issue is very similar to we test this found the phenomena between this stamping to print this liquid alloy surface. If we can make this kind of consider angle and advance is very large, actually make this large. Last time we want to make this smaller can be rolled away. This time we mount this the difference between the static angle and the receding angle is large. So we can very nicely print on this electrolyte on this pedal. We carefully to then micro view for this one. We assume that problem what happened inside. After we mix this water to this pedal, actually we can get a thin film of this water in this micropeanuts on this pedal. So this liquid or water can be gap some of these gaps between these micropeanuts. Is the first thing. The second thing, this thin layer of water make it have a large higher surface tension. It can be form some hydrogen bond between this oxidized layer of liquid alloy to make this filling of this to pin of some kind of liquid alloy on this surface. After that, this surface liquid alloy can be well printed on this surface. You can see here, after this one, you can see this zoomed picture, you can see that liquid alloy can be very rapidly around micro popping line of these rose petals. So after that, we want to show it needs harm to liquid plant. So we test this kind of hydroprinting process. In short time, we found there's no significant difference on this globability. Actually, it's from non-expected point of view. Maybe some problem happened. We just see from the growing, it doesn't affect this one. Another one, we try to make this print this peanut on this peanut. So this very long process, we work this 2 months. We still found it can be work very well. So we use this kind of printing to print this pedal patterns on this pedal of rose. We can use this one to measure the hydration of this pedal, and also at the same time we can print this liquid alloy circuits on the bean sprouts. We can measure the growing of these bean sprouts. Then, as we know, it's very interesting. We can make more attraction. We can make these to control this kind of growth of this plant. So we try to find ways we can control or manipulation the growth of these bean sprouts. Finally, we find if we attach some kind of LED on this bean sprout, we can control very well the growth direction of this bean sprout. So we use a reference bean sprout here. So if we continuous use this kind lighting of LED, you can say this can be can be make this curve as a curve this one. So if you curve if you ignite in long time, the curvature of this one is a bit larger. And also, if we show this reference, the always growing strictly, right? So we use this kind of concept. We try to manipulate the growth of this kind of bean sprout. In next group, so we make a lot of bean sprout grow together and just attach one of these spring bean sprout with LED. So after a few days, you can see the rest of these bean sprout will be try to focus or approach the center one. So this is the first group. The second one, we make this bean sprout with 2 LED. So we we make it nightly, we switch this nightly one time, another one time. So we try to switch this kind of LED one to another one. So we can control this kind of needle. We use this, we can manipulate this beam router to follow the direction of this needle. It's very light. We use this kind of control this beam router to clone this needle. Okay, so just we talk about liquid alloy mutation for what. Then we want to talk about liquid fuse soft robots. So the current soft robots actually there were a lot of working on these soft robots. So I show two kind of robot. One is from the white side group and the robot order group. They make this kind of alternate robot. Another one also from the same group, they also make this one. So you can say, I want to make this untouchable soft robot. They need to make this, I use mechatronic, is very large size one. And also if you want to make this self-contained one, so you can make this one is very slow and is very clumsy something. So we will try to work on this antenna robot. So we try to, if we can combine unique property of liquid properties one, this first work we want to try to work some new kind of liquid driven robot. So I just mentioned antenna design is very important for exploring potential of soft robot because the soft robots the most attractive feature is they can deform, they can work in instrument environment. But if you can't make this antenna, so we're very much limited to its usage. So here we try to summarize a few of these problems with this driving approach for this one. We use this pump, the always suffers from this large print and also very difficult to insert. And also if you want to direct elastomer, you also need to, the problem they need to limit the controllability. And also if you chemical one, was difficult to control and to interpret. So it's possible we can find a method can be perfectly compatible with soft material and enable agile untouched locomotion of soft robots. So we can get inspiration from the lives. So actually there is a kind of bug, growth beer, where actually they work in the and they live in the jungles. When they trapped in the water, they can secrete some kind of material. They can make them automatically move away from this water. And also another one is the soap boat. Soap boat we can work when we play it very young. They can be drive this kind of very fastly. But the problem is this kind of meditation is very slow and also is difficult to control. So we try to make this work. So how we can make this one? Actually, we are very easy to make this one. If we get a more protocol, we use this PMS, we can get this mode, get this one. Then we introduce three kinds of manipulation method. One is we can deposit or deploy the material, the powering material on some kind of place. We can control the direction of that. Another one, we can discrement the deploy this one. Another one, we can use a tape to attach on any kind of robot. You can drive this kind of robot. This one, so we could try to make quite a few of us to make this working. So here we show three kind of molding for this one. So if we can make this one, this we mean is analog mode. If we asymmetrically to deploy the powering material in different ways, we can control the turn direction in different ways. And another thing, we can use digital modes. That means we can selectively make this like a pump or deposition point. We can selectively put some of this with energy material, some material without. So also control the maneuver of these materials. Another thing I just mentioned, we can use this one separately. Make this one, now attach this kind of bolt, make this one. So here we show this kind of manual, and the video can show this three mode how it's working. So here we study how they work this one. So you can see actually they are moving very, very fast. Actually, at the same time, they can very, very fast increase this speed, velocity. That means they are very agile respondement. After that, few times they will come later. So what is the dynamics of this one? Actually, this what happened here. When we make this kind of molecular to put on this water space, this molecule will ultimately live on this material. So when this material living, so the surrounding water will come to compensate this kind of space. So this make this when it comes to they will we introduce this convection come here. This convection flow can be driving this flow here. This is very similar to the team storm, the storm in the teacup. So here on this kind of surface, so because this one usually this surface contact to air, so the heat flux is much larger, so the temperature decrease. So the temperature decrease, so there will be the temperatures then will become colder, they become heavier, they will sink. Then the hot one will be converted this one. This can be get the storm. So this is the driving material is per example is very similar to this one. Here we found a lot of kind of material can be used to the power material. So we can use the many kind of material, for example, span 80, and also this kind of material, for example, PPG, PEG, and PPG. This kind of material is environment friendly, and also we can make kind. Even we can use some kind of biomedical, for example, BSA can be also used in driving materials. And also this kind of velocity or driving can be affected by many kind of parameters. For example, ion concentration, viscosity, mass fraction, and temperature. That means we can find many kind of method to tune and also control the maneuverability of this kind of shop robot. And also, we use this kind of molecule direct to drive this soft robot. That means there is no any mechanical component in this one. That means there will nearly no noise here. So we show here a comparison instrument here. So here is we put our soft robot here. So you can see here the nearly no fluctuation from this noise, right? But we use the similar size of this toy robot. You can say the noise is much higher. That means we can use this kind of strategy. We can build some very low noise one. Another advantage we can show is here. This can be worked on invisible. That means it's totally optically transparent. So you see here, this kind of video, you see here, when we put this robot car here, you nearly can't see nothing. but only you use this kind of um, infrared camera, you can see how to move this one. So this can be very useful if you want to look at this optical transparency, or if you want something application you need to optical transparency, even IR transparency for this kind of things. And another feature also found this kind of robot can be work in the interface between this gasoline and water. So here we show this video, this one can be very well in this nice interface. And also we try to show this interaction for this how we control this one. So this we use this kind of robot come here. So this robot will control this robot. This can be trigger this kind of specific trigger this LED lighting one. Another time we use this swan. So here we make this crossing weak in between this one. We can use a lot of this kind of robot without any kind of noise. We come to together, we can hit this one as soon as possible. We can to assure this important target can be hit to assure high success rate, high precision, use kind of swarm technology. So this is the first story we work about this liquid infused soft robot. Another one we want to talk about is liquid induced multifunctional. So you know the mix multifunctional is the basic for this intelligence. So we show here one of this approach. So you know, in the natural intelligence, for example, it's bacteria, plant, and these animals. They also have this sensitivity, possibility, and sophisticated and agent mobility and great environment adaptability. So they actually very important things. They have these subtle feedback systems. But to make this kind of intelligent robot, you also need this very complicated fabrication technology. For example, this is a white side group. They show this kind of robot. They use 3D or 4D printing, and also this from Jennifer Lewis. They also use 3D printing, and also is from Shen Zhao from MIT. They also use 3D printing. And so another approach is use origami or kirigami. But unfortunately, this origami or kirigami, they are very need a learning curve to make this kind of origami curving. And another approach is we can make this electrical skin, right? We just make this electrical skin on this surface. Then we can also make this more intelligent. But the problem is, if we use this kind of approach, then either could come is denomination between your software body and the electronics part. So here, inspired this kind of work, we try to make this origami, combine this origami and skin technology to make this intelligent software robot. So here is our approach. So first we use laser to pattern this kind of soft robot. So what happened to soft robot? So here, so when we try to pattern to our software, we found this polymer or PMS will become more physical to solvent. When we put some particles inside this solvent, the solvent, for example, we use fur food, this kind of particle can be absorbed, selective absorbed on this kind of rough surface. They can do the same two things at the same time. The first, they can form a very similar process like this origami process. They can make this curved 3D structure. Then the second thing is they can adhesion this kind of surface very very solid on this kind of particle on its surface. So this can be serve as active function on its surface. So after that, we can make this use kind of surface. We can make some active surface on its surface. For example, we can make this actuating part, for example, fairfoot, and also we can make this optical sensor on its surface. And also we can make this thermostat on its surface. And also, very surprised to us, this can be reproducible. When we put this kind of robot, it can be formed to 3D dimension mold. This can be, again, we put it in the solvent. This kind of active part can be dissolved away to come the flat surface, so like this one. We can repeat this whole process to reprogramming this kind of robot can be more adaptive and more smart than before. So this is how we work this selective morphology controls one. So here we show this kind of process. So first one, we make this kind of surface, then use laser. So when you put a drop of this fluid, so this will be partially swell this one. Due to the diffusion gradient, so this kind of will continuous, the solvent will continuous dropping on this one. Even after that, we will evaporate in the air. But the problem is the active particle on this solvent can't penetrate this surface, so will stick on this surface and also to make this three-dimensional one. So we use this design column to show visualization this process. So you can see here clearly on this process. First, make a drop this fluid. So this is dissolving and also evaporating last one. So this shape is fixed, right? After that, okay, is the how we can program this kind of surface. So this after we use these material tools to learn what happened here. So you see here, we use apposition under microscopy. You can see here, this use the element analysis. You can see the major component of iron is stick on this surface. Of course, some of part is embedded inside. Okay. And also, you can see here, this process is a very fast process. We can just finish in about a few minutes. Very importantly, we found this kind of morphine or this kind of three-dimensional forming or origami can be controlled by many kind of this combination of laser operation parameters. For example, the adjacent distance between the laser scanning and also the thickness of this PMS layer. You can see here, we can get this one, they can get a different kind of response. You can see different kind of thickness, they can get a different kind of response for this one. So that means we get a lot of rich parameter we can control. We can get many kind of this is a versatile tool to make this one. So here we show a few of example. So we can use selectively pattern this one. We can get this curvature strand, right? If we can control the roof this one, so we get this windmill shape. And also if we control the degree of this adjacent lines, you can see get this kind of curve one, and this one, and this one, this one, okay? And also we can use this kind of technology to mimic the double strand of DNA. And also, if we change the thickness of the different of this PMS layer, we can get this kind of different these like pedals of daisy, you can say they can get different response under the same magnetic driven. You can say it's we can mimic this daisy flower-like robot. And also, we can make a combination this kind of bending and twisting and plus this morphology mystery. So we can use this same approach of this same shape of this kind of leaf, right? If we use different combination of bending and twisting, we can mimic this tumbleweed-like robot and also mimosa-like robot, right? And also we can make a programming like this, our hand, make this shape of face, okay, victory 6. Okay, now how to make this deformation erase. So here I show this video, this detail process. So first we get this 3D shape, this one. So we immerse in the drawing again. So this will absorption the drawing inside. So due to the anisotropic of this surface, because this surface has large surface, this has a small surface, they will absorb the drawing in different speed. So then we get expanding of this kind of pillar mass. Then the expanding will be introduced the big stress between this particle and this pillar mass. So the particle will be released to the solvent. So after this finish, so we can make this dry in the abdomen eye. So we get this initial state is one. We get this one. So here we use this color and design color run to visualize this kind of process. So this here, we can to watch this video. So you see, we put this one. So then we see this is the process. We put this one. So you can say this is the curved channel, right? Curved this one. We put it in this drawing. Then we totally released. So this will show one particular calculation of redoor press. Actually, this redoor press recovery press also only need a few minutes. So this is a fast process. Actually, this curvaces can be tried. We tried a few times. Actually, we tried a few cycles. We get this one. So this here we show this video. So the process we can show this recovery of this process. This mimosa example is one. We create a relative shape. So this can get this kind of robot. So when you put it in the drawing, it can recover. This also the wind chill shape also can be recovered. And also we kind of feel of this method can be reprogramming this kind of method. For example, we can use add another layer of pillar mass. We can recover this one. We got treating. We get this one. And also if we use very strong laser, we can ablate of this surface, we can get this rehearsal this kind of surface. And also we can use a double surface. We can use another surface to control the original surface, also comes on. But mostly for this has a drawback and also advantage. So I don't discuss detail here. So here show how can make this this reprogramming process. So use here. This we can use configure flower. You can this one. We can make this like we can reconfigure like this like a fan, right? So here this is a shape reprocess, and also we can make this function process. The first material we can make this ferro material. We can get ferro fluid. We can get a magnetic behavior, but we can change this to silver nano wires, and also can be as sensor. And also we can reconfigure with this quantum dot. It can be for the UV responsible for this one. So here we show example how we can reprogram this kind of gate of this robot. So we can see this we can record this one. Just here we can get this warding gate crawling, and also we can get this crawling sideways, and also we can get rolling for this kind of robot. We just use the same this shape, but we can programming with different gate. Another thing is, if we can make this multifunctional on this kind of robot, then we can make different kind of function can be work together to collaborate to make this something new. So here, how we can make this one? This kind of robot, swimming robot. So we tried how to make this one. The top bottom surface, we try to make this hydrophobic, right? So the hydrophobic one can be low friction in the water. And this upper this surface we deposit with this ferro fluid. This can be driving, make this faster. So we can reference this one. So this is the swimming robot. We use this multifunctional with hydrophobic bottom surface and ferro fluid top surface. So this can be run very, very fast. So you can see here, so in this video, so this is our, wait a second. So this is our
we need to hurry up.
one. So this can be work very fast one, but this is reference one. You can say it's very, very slow. That means if you can use multifunctional, you can much higher this performance. Another one we show is multifunctional. We use elimination of UV quantum dot. So this make more like this rainy butterfly. So another one, we try to make this multi-mode locomotion mode for grippers. So we make this kind of gripper, so we can work two mode. One is curling this one. When it's small in this gripper, so carrying the drug is very smooth. So we like this gripper, so we can roll it very fast. But when this drug is very large, we can't grip inside. We can just push to another way, right? So we can very fast to reprogram this very way. So you can have a look at this kind of video, right? So this is the second gate to move this kind of a very big peel.
Zhigang, yeah, we have no time. Yeah, please hurry up.
Okay, I will make faster. Okay. So this is the final demonstration I want to show here. Actually, we just show this kind of frog. They can be many kind of working mode. So due to time limitation, I will not present it too much here. Basically, they have a kind of mode. They can first, if they want to get the temperature is very low, they can go to the sunshine to get the sun shining. After that, if they're overheated, they can move to this cool place to cooling down. Okay, my conclusion mark. So liquid can be play an important role in developing multifunctional for physical artificial intelligence. A second conclusion mark I think is proper co-design or diffusion of diverse functions where fluids can help to implement the advantage of software intelligence. So this is my perspectives. I think if we can use this kind of liquid manipulation and of liquid induced multifunction, we can make this fusion of natural and artificial software intelligence. So finally, I would like to thank to my students. They work very nicely for our work, and also thank you for our supporting financial agencies. Thank you.
Very nice talk. Actually, I enjoy very much for all the results you present here. So there due to the time limitation, we have to go to the question part very quickly. Question one, as Professor Wu, very impressive work. Do you robots swim need energy supply? Looks like it doesn't. Then how long it can work by their own? Zhigang, this was the talk about the.
Thank you. Actually, the energy we can use the warm small. Of course, we need energy. The energy is usually we put a liquid on this surface, on the bottom surface of the robot. And how long it works is dependent on how much fuel we put on this kind of robot. Usually, in our case, we don't put much tank, don't have much tank on this kind of robot. So this just work on few minutes or few seconds. But if you can survive, put a large tank like this, our diesel engine for our car, you can drive very fast and very long. So it's dependent on how much volume of your fuel can be attached on your robot.
Okay, great. Yeah, next question is thanks for sharing smart ideas to print a liquid alloy on the 3D unique surface. You use water as adhesion layers for transfer. How about the water evaporation or absorbed by the plant?
Actually, I think it is very good question. Actually, we use this kind of water to absorb by the plant. Actually, we found that if you the water in long time, the first time when the water attached to on the pedal of rotor, they can attach make this pin on this liquid oil on this on the pedal, but later the water will evaporate. But the problem is, the issue is the liquid alloy has a solid skin. This gallium oxide is solid, so they will be ultimately for this one, they will have to pin the liquid alloy on this surface. So this is a very nice question.
Okay, next question is very interesting. Yeah, so dear Professor Zhigang, yeah, beautiful work. I'm interested in your smart bean sprout experiment. The result are really surprised. Did you think about the future of this technology? Is that possible implant some electronics device for plant? This, for the plant disease like our human beings. That's really, really interesting.
Actually, I need to share again for my screen again. Actually I want to talk about this about topic a bit, but I don't have
Okay.
time.
Okay,
So
go ahead.
actually, my vision was something I think about this one. Actually, if we can use well exploring advantage of this attach some like a tattoo on this plant or any kind of substrate they can be living. They can be living. For example, the most of plant we will see anything on internet. Actually, the plant occupy the most of our planet surface. They not connect with internet. If they can connect to internet and communicate with each other and also can cooperate with each other, we can do a lot of things. For example, we can to control our weather, control our even we can control our environment, and also can do a lot of things. I think that's the
Wow.
future unlimited.
Okay, very, very nice. Thank you, Zhigang. That's a very smart idea. Yeah. So
Thank you.
yeah, we will deliver this certification to you, connect world and universe by your smart, plant. And we're looking forward to all these kind of magic things happening. Yeah.
Thank
So
you.
Zhigang, yeah, that's for you. Thank you very much. Actually, now is the end of today. Yeah, I'm going to thank all of the speakers. Yeah, you know that iCANX talks is global online science talks since and 2020. We have many, many amazing things happening on this. And today is the last version, we have before our Spring Festival. So I have a date statistic here for we start this for start since April, 17th to today. We have totally 40 weeks. Yeah, 40 weeks. We're from, many, many peoples from 5 continents and 12 countries and regions join this talk. And totally 113 speakers and guest hosters get on the stage. And the maximum will weekly is and May 17th, I think, is that week. We have how to announce that 651,000 audience that week. So totally till now we have over 10 million people view iCANX talks. We're really proud of this and proud of your support for this, online science talks. And now we see that iCANX is really an X. Yeah, all these X professors and guests from different places, audience from different places get iCANX happening here. And all the talks and all the discussions really make this technology connect the world and the universe. And now I'm going to share that. Yeah, this was end of the year, and this was a global science talks. We have this. What are we going to have next? So I mentioned that this was our end of our New Year season. So next week and the week after, we'll have 3 weeks break. This was a Spring Festival break. We celebrate the Chinese New Year. And then after this 3 weeks break, we will have our spring seasons, and 2021 will be start on the March 5th. So what's going to happen on March 5th? Let my colleague Paul introduce our new program. Paul, please.
Yes, so we'll be short. We'll after the 3 week break, we'll be shortening the evenings Beijing time a little bit. We'll have one speaker and then follow that with a discussion, and we can tell you who the first few speakers are. Should be coming up on the next slide. We have Professors Hallis, Green, Langer, and Arakawa for a really fantastic series coming up in March. And we've already moved on to filling the April slots as well. So we hope that you'll come back and join us fully refreshed after the break. And I want to thank Professor Alice Zhang for bringing us all together from around the world. And we're delighted to have Jagadish join us as a co-organizer this year. So thank you all, and we wish you a happy new year and break, and we'll look forward to seeing you again afterwards.